All right, guys, as I'm recording this, it's probably about 11:30 at night. I don't even know anymore. My daughter's been puking all night. My wife's been puking all night. That's why I'm not here today. So, we obviously had a lesson to do. So I'm working through it right now. What I'll do with this, obviously there'll be homework attached to this. I'll obviously go over this as much as you need to on Monday. But I'm not going to reteach it from scratch either. So we want to try to get as much out of this as we can. The nice part is you can pause, rewind, review as much as you need. So what we're going to do right now is start really getting into probability. So with probability, we're going to start, and this lesson is all about theoretical probability, which is really pretty basic probability, which is probably why it's the first probability we're doing. So in general, probability is equal to, and the way it's written down here, it says probability is a measure of how blank, if you're looking at the notes. In that case, it's going to be how likely an event is to occur. So what you do is you have this probability of an event, so P of E, and it's equal to desired outcomes, and I mentioned this in the first video I did, but it's desired outcomes divided by total possible outcomes. And that total possible is what we're going to use our counting principle. It's what we're going to use with our combinations, possibly permutations, to help find that total. The desired, we just figure out based on what the situation is, how many outcomes do we like, how many outcomes match what we're looking for, and then we're just going to put that on top. And that is what we call a simple probability. And that really brings up the first kind of event, which is called a simple event. And there's certain examples I'm going to do out of a simple event, but again, it's just the probability of one event, and you'll see that off to the left. But what I'm going to do in this first section, in case you don't have those notes printed out, again, what we're doing right now are simple events. And with simple events, I'm going to start with number 4 as our first example. So with number 4, this is just an example where we have, again, a simple event. That simple event is 2 dice are being rolled. So it says, what is the probability, and I got my notes right here. So what is the probability that the sum of the 2 dice on the next roll is going to be at least 9? So before we are able to do a probability, what we need to do is figure out this denominator. So how many total events, how many numbers are going to go right here? And in this case, we're just going to use our counting principle to do that. We have 2 dice being rolled. So in that situation, we have 2 options that are going to occur here. We have the first roll of the dice and the second roll of the dice. That first roll is going to give us a 6, and that second roll is also going to give us a 6. The reason for that, when I roll the dice, I have 6 numbers the first time. That number is the same the second. It's not like it turns into a 5-sided die. So we have 6 times 6. So this is going to be, for our denominator, our total possible outcomes are going to be 36. And then for the desired, we just have to figure out what we're looking for. And in this case, I want the sum of the dice on the next roll to be at least 9. So if I want it to be at least 9, I want to think about that sum. Like, how do I get 9? So what numbers would I do to get there? So I'll fill those in off to the side here. I'll do that in my numerator. To get at least 9, what you would do is you would just start thinking of some numbers that would give me 9. So I'll start with 6. Now if I have 6 and I want to get at least 9, what we would have in that situation is 6 plus, and if I want at least 9, I got 3. And then I have 6 plus 4, that would give me 9. And then I have 6 plus 5, and 6 plus 6. So right now I have 4 events that would give me at least 9. And here we just have to figure out what those events are. So, and I'll probably go ahead because I'm going to run out of room if I do that. So I'm going to move those down here. As I said, I have 6 and 6, 6 and 5, 6 and 4, and 6 and 3. So that's all the ones if I rolled a 6 first. Now what I want to do now is say, what if I rolled a 5? And I'll go through all those scenarios. So if I rolled a 5 and I want at least 9, I have to go 5, 4. Then I'm going to go 5, 5. And then I'm going to go 5, 6. So if I rolled a 5, those are my options there. You notice you'll see a pattern to this as I work my way through it. Next, I'm going to go with a 4. So let's say I had a 4 first. So here I can get a 4 and I want at least 9. So I'm going to have 4, 5 and 4, 6. And lastly, if I rolled a 3, the only way to get 9, I'd have to roll a 6 that second time around. So you take a look at all these options. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So my numerator is going to be 10. So all you have to do at this point is simplify that probability. And if you simplify that, I mean, you have 10 over 36. You can divide the top and bottom by 2. So that would be 5 on top and 18 on bottom. And that's going to be your probability. And that is a probability, just a simple event. Doesn't seem so simple, but that is the process. I said, use your counting principle on the bottom and just figure out the top. If you have to write them out, and just write the probability at that point. So moving on again, just going through different types of events here. I'll now move on to number 5. So number 5, they sent what's the probability of drawing a heart or a club from a standard deck of cards. Now what I should be doing down here is putting out a picture of an entire deck of cards, but there's 4 decks. And there's a lot of questions really in dealing with probability that deals with decks of cards. It's just a really good way to test and learn about probability. So the types of cards, and I'm not even really a card player, but I know we have our diamonds, we have our spades, we have our hearts, and our clubs. So there's 4 types of cards, and there's 52 cards in an entire deck. And this is just if you don't know, you can see the picture. So you can see, if you see the picture, so I don't have to write it all out. It goes from aces all the way, or really if you call it aces, but deuces. So 2 through 2 through 10, and then you got your jack, queen, king, king, ace. So when you really look at it, you have your each type of card, and there's going to be 13 of each. So we have 13 of each of these. And that's going to add up to 52 cards. So really, once you kind of figure that out, you're good. You also know that 2 of them are red, 2 of them are black, and it really, there's a lot of cool little probability concepts that you can really test on that. So anyway, in this situation, we have the probability of drawing a heart or a club from a standard deck of cards. So a heart, we have 13 hearts, and a club, we have 13 clubs. So this one is very straightforward once you get figure out the deck here. We have desired outcomes, so the probability of this event, I didn't write that last time, but the probability of that event occurring is going to be desired outcomes, which is 26, over total possible outcomes, which in this case is 52, and you can simplify that to 1/2. And that would be your simple event for a deck of cards, which is a very common question. Expect to see some more of those. But again, notice, same question. The only difference here is finding that desired outcome was real quick, and the total possible outcome, we knew the total possible outcome, so I didn't have to do any counting principles. And again, you just apply them when you need to. So those are skills, those prerequisite skills you need to apply at the right times. And then the last one, number 6, which I'll just go ahead and put in right here. So with number 6, what we're going to do here, we have 8 books lettered A through H. I'll go ahead and write those letters out. So we have A, B, C, D, E, F, G, and H. So I have my 8 books that are lettered A through H. Okay, and I have them written out here. If Scott randomly chose 2 books, so I'm actually taking 2 out of that group, what's the probability that he chose books A and B? So in this situation, I know my desired outcome. I want A and B. That's it. So my desired outcome, when I'm doing this probability, I know the numerator is going to be 1. However, that denominator, we need to think about this. I'm taking a group of 8 items, that's my total sample size, and I'm pulling out, I want to figure out the total possible ways to pull out 2 items from this 8. We just did that. That's called a combination, because the order won't matter when I do this, because if I can have A, B, or B or A, it doesn't matter. So my denominator is going to be a combination where N is 8 and R is 2. Because again, in this scenario, I have 8 items, I'm pulling 2 out. I'm going to get a group of 2, and the order doesn't matter, which makes that a combination. So that's where that combination is going to come in here. So we are just really going to go ahead and work this out, see what we get. Remember, this is 8 factorial over R factorial, which is 2 factorial, times 8 minus 2, or N minus R factorial, so 6 factorial. So again, I know my numerator is going to equal 1. I'm good there. I'm just simplifying this denominator. Now remember, this is going to be 8 times 7 times 6 factorial over 2 factorial times 6 factorial. This is part of that simplification process. So I'm going to take this, cancel out my 6 factorials. I'll bring these back down here. I now have 1 divided by 8 times 7 over 2. Remember, 2 factorial is 2 times 1. Therefore, I can just write it as 2 because I know that's what 2 factorial equals. Simplify a little bit more. So this becomes 1 over 4 times 7. That's over 1, so this really doesn't matter anymore. 4 times 7 is 28. And that's probability using combinations. So that is going to be your simple events. All right, guys, the next thing that we're doing is a complement of event. Now, if you have a simple event, you know, the complement, and I'm going to just write the formula out. I'll explain, if you have the notes, what to fill in here. But a complement of an event is the probability that an event is not, that's what we should be filling in, event is not happening. Now, if you really want to simplify this down quite a bit, it's really at that bottom piece. This is what we write. The complement of an event is the probability of what's called not E. So that means the probability that an event will not happen. You probably saw this little symbol before in geometry with your if-then statements and things like that. But this is just going to equal 1, which is the probability of everything happening. And if we want to figure out what the probability of something not happening is, we take the total and we subtract the probability of the event actually happening. For example, if I just use it as a percentage, the probability of something occurring is 60%, then the probability of it not occurring is 1 minus 60, or 100% minus 60%, which is 40%. So it's just the opposite of that. And that's really all we're going to do on these. And I'm only going to do for this one number 7 and number 10. So I'm going to start here with number 7. And it says, what's the probability that it will snow tomorrow is 7 out of 20. So that means the probability of an event occurring, in this case, is 7 over 20. So what we're saying here is, what is the probability that it will not snow? So this is a very basic, simple one. So the probability of it not occurring, so that's what we're looking at here. Well, it's going to be 1, the total. So 1 minus 7 over 20. So you take away what the probability of it actually happening, and you're left with the probability of it not happening. So here I would probably write that as a fraction. That's probably the easiest way to look at this. Multiply the top and bottom by 20, and you're going to get, in this case, 20 minus 7 over 20, which is 13/7, or 13 over 20, sorry. So that's the probability of it not happening. Very straightforward if you think about it, just subtracting. And then number 10, I'll do that one right down here. So for number 10, it says 2 dice are rolled. So what is the probability of not getting a double? So what we want to do is figure out what's the probability of the event actually happening. In this case, the event is getting a double. I want to know what that probability is. So remember, with the dice, we kind of need to work these out. So in this situation, I want to just kind of figure out how many desired outcomes do I have. So we have 1 and 1. We have 2 and 2. We have 3 and 3. You probably get the idea. And those are going to be your doubles. So you can kind of look at this. The probability of this actually occurring is going to equal 5, not 5 actually, sorry. We're looking more like 6 out of 36. I want the probability of it not occurring. So I want the probability of that not happening. So we're just going to go 1 minus 6 over 36. Again, you can get that common denominator. You just multiply, in this case, the top and bottom by 36, and you end up with this. You're going to get 36 minus 6 over 36, which is 30 over 36, which we can simplify. Again, divide by 2, that's 15 over 18. And actually, I can divide that some more. I could have picked something better, but I didn't see it right away. But I can also divide, in this case, by 3. 15 divided by 3 is 5. 18 divided by 3 is 6. So that probability is going to end up being 5 out of 6. That's the probability that we do not get any doubles. So what this is going to do is now lead us into our next topic, which is going to be compound events. And this is taking these simple probabilities, single. Really, when you think of simple, we're talking about single probabilities and doing a probability on top of another one. So what's the event of A, then B occurring? So those are going to be our compound events. So at this point, I'm just going to go ahead and kind of get a line right in here to separate these two. So we're kind of moving on over here. And we're going to now be in the concept of compound events. Okay. So with the compound events, there are 2 types, and the first one, you can kind of see the boxes here, and I'm just really reading from the boxes at this point. So again, it's really nice if you assume that you have the notes already printed. But when we're dealing with an independent event, that's when the outcome of an event does not affect the outcome of the other. In a way, when you're doing these examples, you don't need to really know which one you're dealing with, if it's called independent or dependent, but they do make sense. If you think of the word dependent, it's depending on something else. So a dependent event is when the outcome of an event does not affect the outcome of the other. So when I show you these examples, you'll see that these words, they make sense when you see it, but you don't really need to know that. But I'll start with some examples of independent events, and then again, these are ones that are independent of each other. And you'll see what I mean when I show the examples on this. So what we'll do is I'll start with number 12. So starting with number 12, you'll see we got a coin is tossed, then a day of the week is selected. Now notice, these things are not related at all. One doesn't affect the other. So when a coin is tossed, the day of the week is selected, what's the probability of getting tails, then getting a day starting with the letter T? So we have 2 events, and that's where we get a compound event. There's 2 probabilities being combined. So what we're going to do with these, in both of these, we are going to be multiplying these probabilities. So in number 12, you're going to see, and this is what you'll see with, and I'll put the note up here, if it's independent. So we have an independent event, and this is what I have here. What we're doing is we're going to take our probabilities, the probability of A occurring times the probability of B occurring. You can put that in the box on the top of your notes up there. That's the independent event. So that's a probability of event A happening and then probability of event B happening. And again, these are independent of each other. So you're going to see in this case, that's exactly what I'm going to do. I have my coin that I'm flipping. The probability of getting a tails is going to be 1 out of 2. So that's the first probability. Multiply that by the probability of picking a day with the letter T. It starts with the letter T, so Tuesday and Thursday. Okay, so there's 2 days that start with the letter T, and that's 2 sevens. Again, we think about these separately, but we're trying to have them happen back to back. So in this case, we can actually cross cancel here, and we get a probability of both of those occurring back to back of 1/7. So that's going to be a compound event, an independent compound event. Multiply your probabilities. We've got a couple other ones that I'm going to do here, starting with 14. And you'll see when you get to 14, we have this situation, and we'll use this on 18, 14, 16, 18, and 20. So we're going to go through this whole section doing this. So in this entire section, I'll put this off to the side as well, and I'll try to kind of figure out the space we'll be using, something like that. But in this case, we have 8 red crowns, so 8 red. We have 14 purple. We have 6 yellow and 4 green. Now, because we're doing probability, I probably want to get that total. So that's we add those up. What do we got? 32. Yes, we got 32 of these. So there's 32 total crayons that we're working with. So in this case, what they're saying is a crayon is selected, replaced, which means we're putting it back in that pile. That's super important. So we're going to put it back in that pile, and then we're going to pick another crayon. And again, for independent events, we're going to have a situation where we pick a green and then we pick a red. Because we're replacing it, they are completely independent of each other because we have the same set of crayons when we go to pull that second one, because since we replaced it, it went back and we are back to where we began. So if I want to get a probability, in this case it's written out for us, of green then red, so green then red, what we do is just find the probability of green, so 4 out of 32, times the probability of a red, which is 8 out of 32, and we just multiply these. Now I want to simplify this as much as I can. I know 4 goes into 32, 8, 9. So we're going 8 times for this one. So we're going to go 1 out of 8. Over here, we have 8 out of 32. Well, 8 goes into 32 4 times. So 1 over 4. So we have 1/8 times 1/4, which is 1 over 32. So the probability of those happening in succession, like one after another, is 1 out of 32. Obviously the odds are going to go down when you need 2 things to happen back to back. So when we do 16, I want to get 2 yellows. So I'm going to look at this one. I have my 2 yellows. Again, there's 6 of them. So I'm going to have 6 out of 32, and then I'm replacing it. So that means at this point, it's an independent event because they are not related at all because I've replaced it. I'm dealing with the same situation. So we're going to multiply by 6 over 32 yet again. And in this case, we are going to, if you multiply everything out, you simplify it. I can cancel some things out here, but basically, long story short, this is 9 out of, because I've already done it, 256. Again, that's just multiplying, simplifying, and whatever you need to do with it. So again, let's take this situation, and now I want to talk about a dependent event. So I'm going to try, most of my colors kind of look the same here, but I'll try to switch colors. So we have a dependent event. What we're going to do for dependent, the way this works, and this can go in that box up at the top, we do the probability of A occurring, and we're still multiplying. The only thing we're doing differently when we multiply here is that these events are dependent on each other, and you'll notice it's the probability of B, it's times the probability of B occurring after A. And again, that should matter. If you're doing a dependent event, it should matter. Somehow A should affect B. And this easy way to make this happen is to kind of show this correlation between these two problems. And then let's do 18. And you'll see how this one is a dependent event. And the reason is, in this case, notice the note on the top. It says, using the same example from above, which is what we're doing, assume once a crayon is selected, it is not replaced. So now that's going to affect my next probability, my next situation, because I have fewer crayons to choose from. So now I want to get the probability of a purple, then a green. Now again, the difference on this one, when I get my purple, nothing changes there. That's going to be 14 out of 32. I'm going to multiply by my next probability, but here's the difference. It's now out of 31 because I'm not replacing it. That's how they're dependent on each other. That's why I said when I talked about independent and dependent, this is what I meant. With the dependent, it makes sense. These depend on one another. Whatever happens here is going to affect this guy. So that situation, I'm pulling then a green. So my green is 4. So I have 4 out of 31. But again, that number is the same, but that one's not. So now I multiply these. Again, you can simplify, do what you need to do. But this is going to be 7 out of 124. So again, same situation, but this is what's happening. Independent, we don't replace, or we replace. Dependent, we're not replacing. That kind of affects the next event from when it occurs. And then we get to number 20, same situation. We have probability of 2 greens. So probability of green and then green. So I want those two to occur in succession. So here I have my greens. I have 4 out of 32 times, and now not only are we not replacing, so we're going to have 31 crayons now, but we've already pulled that 4 out, which means we pulled one of the 4 out, which means we now have 3 crayons that are green left. So that's going to be 3 out of 31. See how those are dependent on each other. So we multiply those together and simplify. It's 3 out of 248. Once you simplify the fraction and do all the stuff that you need to do. So to kind of wrap this up, I don't really have much room here, but I want to do one more if I can squeeze it in. Remember, these were all related. I really don't have much room. This may have gotten cut off a little bit, but the last one I'm going to do is number 21, and just kind of let me squeeze it in right here. I'll do a different color. It kind of stands out in the corner. So this one we have the cards again. I just want to do one more card problem. So we have a card is drawn from a standard deck, not replaced. That's the key, not replaced. That's what's going to make it dependent. And another is drawn. So what's the probability of choosing a heart then a spade? So when I had the hearts and the spades, remember there were 13 of each. So I have my hearts, which I have 13, and I have my spades, which I can't draw a spade, so I'll just write the word spade. But there's 13 of those. So we have 13 hearts, 13 spades out of 52 total cards. So I want to first get a heart, and then I want to get a spade. So I'm going to have 13 out of 52, but again, I'm pulling out that card and I'm not replacing it. So my next number is out of 51. Well, there's 13 spades. So that's going to still be a 13. And we're just going to multiply those two numbers together, simplify as we needed to. And this is going to simplify out to 13 out of 204. Again, that involves some simplifying. Use a little bit of calculator if you need to as well. So as you can see, probability is still a lot of multiplying. It's kind of like the counting principle. We just do with probability as well. We multiply probabilities. And like I say, there are different types of probabilities, but they are kind of related in the process. We just multiply the probabilities together. You need to pay attention to what we're multiplying together. If you can do that, you're going to do awesome. And good luck. I'll see you guys on Monday, hopefully.